Welcome back. You made it so far so good through the course of elementary statistics. We're going to pick up one topic today from chapter 2, mainly expectations. And a little bit on variation, the variance as well. Alright, so here's kind of the way expectations work. Um, let's see. What's an easy, simple one? So let's say we have a commute. Um, X is the average time we have to commute. Maybe average commute time to work or something like that. Okay, and we'll say that the expected value of X, we'll go ahead and say is, we'll call it 18 minutes. If I know the expected value, and I want to get more into the expected value, but first I want to show you some of its properties. Suppose we're interested in the entire week. So this is just on any given day, we're expecting 18 minutes of commute time to work. So if we're given the entire week, we've got five of these x's. Or what? Or w equals 5x. Well, if we're interested in the expectation of w, which is really the expectation of 5x, right? All I'm doing is saying w is the same as 5x. Saying I have 5 days, and I want to know the expected time in the entire week. Expectation is really nice in the sense that this 5 is a constant that can just come out. And what we're left with is the expected value of x. So this is just 5 times the expected value of average commute time to work. Or I guess x shouldn't be average time, commute time to work. So we know what this is. It's 18. So 5 times 18, we put that in, and we should get 90. So for the entire week, we get 90 minutes of commute time. Alright. Okay, now let's look at expected value a little bit more. So let's say we're rolling some dice here. We got the options of 1, 2, 3, 4, 5, and 6. So these are the possible outcomes, these xi's. Or this is x1, x2, x3, x4, x5, and x6. So these are the possible outcomes, and these are the probabilities for those outcomes. Probability of x. So the probability of rolling a 1 is always 1 out of 6. Probability of rolling a 2 is 1 out of 6. Etc. They were all 1 out of 6, right? Because they're all equally likely. Rolling a 4, there's 1 4 out of 6 possibilities, and each possibility is equally likely. So what I've drawn here makes up what is known as probability distribution for rolling a dice. I have all the outcomes and their associated probabilities. So you'll find in your textbook something that looks like this. The expected value of x is equal to this kind of thing. Xi times the probability of xi. I is equal, well, I is in sample space. Let me explain this. Really all it is if I want to know the expected roll of the dice, the expected outcome on the dice, what I would do, I would take each one of these, there's 6 of them, right? and I would multiply by their associated probabilities and add them up. So this would be x1 times the probability of x1 plus x2 times the probability of x2, etc. All the way up to plus x6 times the probability of x. So what that ends up giving us is what? This was 1. 1 times 1/6 plus rolling a 2, the value of the 2 is 2, times its probability, plus the probability of getting a 3 times 3, plus the value 4 times the probability of rolling a 4, and plus 5 times the probability of rolling a 5, and I'll do it down here. Also plus 6 times 26. Okay, so do you add all these things up? Well, let's just go through it just to make sure we know how to do this. 1/6 plus 2/6 plus 3/6 plus 6/6. Yeah, that's what this is. So you add all these things up, you're gonna get what is it? 7, 14, 21, 21, 21 over 6. So this really comes down to 3 and 3/6, or 3.5. So what does this mean? This is the expected value for rolling a dice. Expected is sort of what what will happen most often, or maybe better than that, what happens, uh, the distance from this value is going to minimize that. Of course, we're not going to roll a 3.5, that's not realistic. Sometimes the expectation is realistic, we get a whole number, like we did with commute time. And here, this is not a possible outcome. It's just smack down halfway between all the data points. It's the median of this data. And that has to do because they're actually equally likely. We could change this slightly. So let's say we have 1, 2, 3, 4. Maybe on our die this time, what we'll have is, instead of having a 5 and a 6 on there, we'll replace the 5 with a 1 and the 6 with a 1. So these are the xi's. So if I replace the 5 with the 1 and the 6 with the 1, then I've got 3 ones on the die, 3 out of 6. The rest are just all 1 out of 6, right? And if I want to get the expectation of this, it's just 1 times 3 over 6, plus 2 times 1 over 6, plus 3 times 1 over 6, plus 4 times 1 over 6. You add all these things up, you should get 3, 4, 3, 5, 6, 7, 8, 9, 10, 11, 12. 12 over 6, which is a 2, which is something that can happen. So more often than not, we're likely to see something lower. It's not saying that obviously 2 is not the most likely. It's not what we're saying here. Expectation is sort of like an average, sort of like a central tendency. It's kind of like the mean. In fact, that's what we call it. We call it the mean. Okay. Moving on. So if I know the expectation of x is 2, if I give you this, the really nice thing about this, let's say I have 3x plus 1. The expectation of this, again, has this nice property called linear property. X plus 1. So the only thing that's interesting here is the random variable x. The 3 comes out, and well, really what we have, I suppose, is it comes on to each term. The expectation of 3x and plus the expectation of 1. The 3 comes out, and you have the expectation of 1. Continuing, the expectation of x is 2. The expectation of 1. This is not a random variable. So the expectation of any constant is just that constant. It seems to make sense, right? There's no randomness involved. It's just going to be that one constant. So this is 6 plus 1 or 7. Okay? And similarly, if this was y, for instance, we just have a y here. You would have to actually compute this if that was a random variable. Okay? This is useful in gambling and things like that, as far as finding a fair price. So we could say, okay, we've got this game. Where if you roll, so we'll stick with the dice. If you roll an even, you get $2. If you roll a 1, you get $5. And if you roll a let's go with if you roll a 6, you pay $1. So this is good. You're in the bonus here. This is the jackpot. And then if you roll a 6, you have to pay some money. Okay, so these are the outcomes in our game. So this would be our x1 here, x2, and x3. Okay, so let's see. What is the probability of winning $2? Well, we have to roll an even, right? It's going to be the value 2 times the probability of this. Even, there are 3 of them, 2, 4, and 6, out of a total of 6. Now let's move on to this one. The value here is $5, and its probability is rolling a 1 is 1 out of 6. Moving on to the last one, we have to pay $1. So this is actually a -1, or a -1, either way you'd like to think about it. And the probability of rolling a 6 is 1 out of 6. So this is the expectation of winning. So if you multiply this out, you'll get 6 over 6 plus 5 over 6 minus 1 6, which gives you 6 plus 5 is 11, minus 1 is 10, 10 6. So that's 1 and 4 6, or 1.66 repeating. So the fair price for this game would be pay $1.67. Why? Because we expect the average person, more often than not, this is sort of the mean. So this would be the fair price for this game. Okay, so that's a gambling situation. Real quick, I'll show you sort of a variance kind of thing. Variance is a little bit different. It's not quite linear. So when I do have something like this, variance of 3x plus 1, so let's go to this similar problem that we had before. Okay, so what will happen is it will actually be 3 squared variance of x plus the variance of 1. So this would be 9 times the variance of x. In here I would have to tell you what the variance of x is. The variance of 1, again, 1, there's nothing random about it, so it's not going to vary at all. There's no variation at all. So this would just be 0. Of course, we don't have to write this. So it's not quite linear. It's linear, it's close to linear in the sense that we can apply it to this, and we can apply it to that, but these constants that we move out become squared. Okay? If you wanted to read more in your book about that, actually, I will go ahead and just do one more example here. Let's say we have a portfolio. We've got some Google stock, and we've got some Exxon stock. We've got the mean, which is our expectation, what we expect, and we've got our standard deviation. So we're going to fill these in: 0.105, 0.011, 0.0056, and also 0.0506. No, sorry. So let's say we have a portfolio with 6,000 shares of Google and 2,000 shares of Exxon. So if I wanted to know the expectation here, what is the expectation in my portfolio? It would be 6,000Z. I'm sorry, plus 2,000 times what I expect to get from Exxon. So again, splitting this up, I'd have expectation of 6,000Z plus the expectation of 2,000E, and then these constants can come out front. So what do we have? We have 6,000 times the mean here, which is 0.011 for Google, plus 2,000 times the expectation for Exxon. We expect 0.0056 on our return. So you would multiply these two and multiply these two, add them together, you get your expectation. Let's look at what if I wanted to know the variance of this portfolio. What would be the variance of my outcome? The variance of, again, we have 6,000 shares of Google plus 2,000 shares of Exxon. And so this works similarly. The variance of 6,000G plus the variance of 2,000E. And by doing this, I'm going ahead and assuming that Google and Exxon are independent. At least in this course, that will always be the case. If not, then this formula ends up being a little bit different. But you can go ahead and assume that everything that you'll be dealing with, the variables will be independent. And it seems like it should be independent. Why should Google shares affect Exxon? They're not even closely related. Okay, so let's go ahead and pull out these constants then. Keep in mind, with variance, when you pull them out, you have to square them. Variance of G plus 2,000 squared times the variance of B. So you get this number times the variance of G, which was, this is the standard deviation here, right? 0.105. Square it, that will give you the variance. Right. 2,000 squared, the variance of E. I don't have the variance of Exxon, I have the standard deviation. Square it, and that should give me the variance. So you square this, you square that, multiply them together, square this, square that, multiply them together, add them all up, and you should get your, that would be the variance of your portfolio in dollars. Okay, so that pretty much wraps it up for chapter 2. I think we're probably going to be fine going into chapter 3 now. Okay, chapter 3. So finally, we kind of get into this notion of a random variable that's not equally likely. So we're getting away from this probability that's just as similar as the number of outcomes we're interested in over the total number of outcomes. We're getting away from this proportion. Okay, so if I draw the distribution of normal random variables. I'll go ahead and start with this thing called a standard normal variable. Standard normal. And here's more or less what it looks like. 1, 2, 3, 2, 3, negative 1, negative 2, negative 3. It looks about like this. And this is the area underneath this curve. The area underneath this curve represents the probability. So you can see what's going on here. Half the data lies below 0, half the data lies above 0. This is symmetrical. So the probability that I get something less than negative 2 is the same as the probability of getting more than positive 2. Meaning the area here is equal to the area here. Okay. So less than 0, we have 50% chance lying to the left of 0, or less than 0, 50% chance lying above it. Standard normal has this property where the mean, or you can write this Greek letter, is equal to 0, and the standard deviation, or this thing, is equal to 1. So these little dots out here, this is 1 standard deviation, 2 standard deviations, 3 standard deviations, 1 standard deviation, 2 standard deviations, 3 standard deviations from the mean. Okay, so this is your typical one, your typical normal. Of course, it doesn't always look like this. It might have something that looks a little more like this. Go ahead and put 19 here. 3, 3, 23, 7, and 31. 15, 11, and 7. So this is not your standard normal. It does not have a mean of 0. It does not have a standard deviation of 1. So just briefly, I can kind of show you how we can take this and convert it to the standard normal. And this will be really useful. We have a chart for a standard normal, and we'll use that for all of our probabilities. Alright, so let's go ahead and take this thing. So here's the mean. The mean here is 19. And it looks to me like the standard deviation is 4 here. So this is a normal curve with a mean of 19 and standard deviation of 4. So if this is my x, this is my x is normal with these things, then what I can do is from this x, I can subtract off the mean. I can subtract off 19. Now if I do that, what happens to 7? 7 minus 19 gives me negative 12. 11 minus 19 gives me negative 7. Wait. 11 minus 19 is, negative 8. 15 minus 19 gives me negative 4. 19 minus 19 gives me 0. 23 minus 19 gives me positive 4. 27 minus 19 gives me 8. And 31 minus 19 gives me positive 12. So if I end up subtracting this off, x minus 19, this is the curve here. This has a mean of 0, but the standard deviation is not quite right. As it turns out, if I do one more thing to this, where I subtract off this 19, and divide by the standard deviation, you can see I'll get this normal curve again. So if I divide this by 4, I get negative 3. This by negative 8 divided by 4, I get negative 2. Negative 1, 0, 1, 2, and 3. And so that's the way we transform this thing. So what I have here, the transformation, this is called the z-score. And if you want to write the general way, or general form, the z-score is written as x So these are your variable, your x, which you observe, minus the mean, divided by the standard deviation. And again, so all this does is it shifts the mean to 0 by subtracting here, and dividing by the standard deviation sets it so the standard deviation is actually goes to back to 1. It just scales it. Okay? So the z-score. So I can take this normal variable and transform it using this transformation into a standard normal variable. That is one with mean of 0 and a standard deviation of 1. We're going to use this z-score a couple other ways before we do get into this probability. But I thought this was sort of a neat way to kind of show you how this transformation works. Okay, let's go ahead and say we got an ACT score of 24, and we'll say that ACT scores are normal with a mean of 21 and a standard deviation of 2. And we'll say we got a SAT score of, let's say, what is the SAT score now? I think they're normal. Let's go with 1200 and the standard deviation of 150. Okay, so if we get let's say 1300, so we can tell the ACT score is above the mean, the SAT score is above the mean. We want to know which students did better. Alright, so the way we can actually compare the student 1 to student 2, we can standardize it. So let's standardize the first one. So let's use the z-score here, which is x minus the mean divided by the standard deviation. So for the first one, for the ACT score, we have 24. This is what we observed. We got 24 from the first student, minus 21, all divided by the standard deviation here, which was 2. So this gives me 3 over 2, or 1.5. So what this means is that this student scored 1.5 standard deviations above the normal. So he's scored right here. Okay, let's go ahead and transform the other one. That's student 1. And then we can compare them. So we have a 1300. The z-score here is going to be same formula. So it's going to be what you observe, which we observed at 1300, minus the mean here, which is 1200, all divided by the standard deviation, which is 150. Once we actually compute this, we get 100 over 150, which is just 0.66 repeating, or 2/3. So the second student scored about here. So we can already tell, yes, the first student actually did better. He scored higher compared to the national mean than the second student did compared to the national mean. So z-scores are useful just for comparison's sake as well. Okay. I think now is the time to start getting into using your probability table to actually find these probabilities. Okay, so let's start with something simple. Let's start with probabilities of standard normal. So I'll use z as a standard normal variable. Normal with mean of 0 and standard deviation of 1, standard normal. We'll start with this. Let's look at the probability that z is greater than 1.5. Okay, so what this means, we've got this graph 1, 2, 3, 1, 2, 3. 1.5 is about here, right? And we want to know this shaded region. This shaded region will tell us the probability here. Okay? So what you'll have to do is you can use your book. There's a table in there of all the standard normal variables. It looks like it's on page 362 for you, and 363 as well. If you look here, here's what they give you. They give you the shaded region here. And they give you the shaded region here as well. So these are values to the left of the mean, these are values for values to the right. So if I have less than 0, I'm going to be using these. If I have greater than 0, I'm using these. You won't find them if you actually look for it in the wrong table. So shouldn't be any confusion. Well, there's a problem because the table gives us the area below this, right? The table gives us this. So let's go ahead and find this in the table. Here's how you'll use it. Let's see if I can't turn this back. At least pull this up. I'll tell you what, the easiest way to do this, since this is 1.5, we're looking at this area. We said this thing is symmetric. So it's the same thing as the area less than negative 1.5, right? Just because it's symmetrical about 0. So here, I'll show you where negative 1.5 is. So what you would do is you would find on the right here, you have 3.4, negative 3.3. You go all the way down to negative 1.5. These numbers across, you can see these are for the hundreds. So we had exactly negative 1.50. So you find here's negative 1.5. There's negative 0. So you trace them down and you find this thing is 0.0668. Again, it's just this one right here. Okay? 0.0668. So the probability of getting higher than that is 6.68%. Again, but this is just so you know what you're finding. All your answers will be put into this decimal form. Probability is between 0 and 1, right? Okay, let's do another one. Let's find the probability that z is less than negative 1.23. Okay, so you'll use your table. You'll find this negative 1.2. Negative 1.2 is about there. And we have negative 1.23, so we have 0, 0, 0, 1, 0, 2, 0, 3. This time it's up here. And when you come across, you can find where these two meet. So they meet at this value, which is 0.1093. So you see how that works? It just kind of comes down here. 0.1093. Again, if you're unsure, just draw the graph. -1, 1, -2, 2. This thing is here at -1.23. We're looking for this area less than this, which is what this graph is giving us. So that's fine. On the other one, we had the area above it, so that's why we used this symmetry. Okay. All right. So let's go ahead and move on to something that's not standard normal. Let's say we have the standard normal variable of 1500 is the mean, and standard deviation is 300. We would like to know what is the probability that x is greater than 1500. Well, this is not standard normal, so you cannot use your chart for this. You're not going to see anywhere close to 1500 on this. But what you can do is you can standardize it using this formula that we have. X minus the mean over the standard deviation. So, what you end up doing is, this is the same thing as probability of z, a standard normal variable, being greater than, again, this is 1500, that's what we observed. We're going to subtract off the mean here, which is 1500, and divide by the standard deviation, which is 300. So this gives us the probability of z, which is standard normal, is greater than 0 divided by 300, which is just 0. And we don't even really need our chart for this one. If it's symmetrical, half of it is above it, half of it is below. So this thing is certainly half, 0.5. You can check this at home in your book. Let's use the same data though, and say, where's the probability? Let's do an interesting one. Right after this. Less than 1400. Alright. So again, let's go ahead and standardize this. This is the same thing as the probability that z is less than 1400, which is what we observed, minus the 1500, all divided by 300. So this is negative 100 over 300, or negative 1/3 once you simplify it. When you're using your chart, you'll notice that you do have to convert this to a fraction. This is just 1 divided by 3. So you have this sort of thing. So we can draw our picture and kind of see what was going on here. We've got 0, 1, 2, 3, somewhere around here. And we're looking for the area that's less than this. So this is good. It matches up with our graph very well. The chart that's given to us gives us that area, so we don't have anything to do with this. If you do look for this, we're looking for 0.3. So on here, we look for 0.3. It's down here at the bottom. And if you look across, we only have the hundredths. So if you have something like this, go ahead and round it to the nearest hundredth. Here it's just going to be 0.33. That's the best we can do. So if you round it to 0.33, you've got this negative 0.3 here, and 0.03 there. And when you come together, you should come up with 0.3707. So the probability here is 0.3707. Okay, so we can do one more kind of variation here. We've seen them above, we've seen them below. Let's go ahead and look at something that's in between. So let's go ahead and use the same kind of example. Let's see that x is normal with mean of 1500 and standard deviation of 300. And we want to know the probability that someone scores in between 1400 and 1700. Okay, if I have something like this, here's how we'll do it. I will standardize each of these. So again, let's just subtract off the mean, divide by the standard deviation. So subtract 1500 off, divide by 300, less than b, less than 1700 minus 1500 divided by 300. So what's our probability? We have negative 1/3 over here is less than z is less than positive 2/3. Alright, again, if we're going to convert these to decimals, rounded to the nearest hundredth, we have negative 0.33 less than z less than 0 positive 0.66. Okay, so let's go ahead and see what this graph looks like. Okay, so we've got negative 3/3, negative 1/3 here, and positive 2/3 there. And what we're interested in is the area in between these two points. So this is a little bit different than what we had before. They have the area that's below it. Well, if you need to find the area between these 2 points, what you'll end up doing is you'll find each one, you'll look each one up, you'll find a value for this one, you'll find a value for that one, and if you subtract them, you'll get the area in between them. So anytime you have the area in between, you end up subtracting them. Should be pretty straightforward there, I think. So 0.33 we found before, maybe 0.33 less than that is for this one we found 0.3707, and for 0.66 positive 0.66 and 0.606 is 7.454. I'm sorry, 0.7454. So the area in between here is subtracting these two. So we get 7, 4. So this is the area in between. So the probability of scoring between 1400 and 1700 on this exam we found was 37.47%. Not too bad, right? So again, if you have something that's above it, you can reflect it and use the negatives. If you have below it, perfect, we don't have to do anything. If you have this space in between, what we'll do is we'll find each one and we'll subtract them. Okay. So we've seen some power here as far as transforming them. Should be able to do everything else. We're going to go ahead and skip this normal approximation, normal probability plot, and we'll get straight into 3.3 and 3.4. Okay. So let's see. Next up we have something called the Bernoulli trial. The Bernoulli trial is really basic. It's just you have some kind of test or some kind of event, and you have two possible outcomes. Two possible outcomes. That's it. All right. So you have maybe this probability for success. They call it P of success, and Q, or 1 minus P, probability of failure. I think your book actually uses this 1 minus P. If you do go online and try to find some other resources and look into it, you'll see this Q, and that's what this means. When you have two probabilities, it's sort of P is always given as the probability of success. But think about it, you have one other possibility, right? Well, this is, maybe if we have a heads tails kind of thing, probability of flipping heads is 1/2. So what's the probability of the other event? It's going to be the complement of that, right? So Q is sort of the complement of that thing, or this failure. So it's as simply as that. Bernoulli trial, and what we'll see is we'll use those into our next two distributions. So these are going to be the normal distribution was continuous. You could have any kind of number we wanted. We're going to go back to discrete. Okay. So here's this case. So just to clarify, let's say we have a heads and a tails. Flipping a coin, you have two possible outcomes. The probability of flipping that is not going to change. It's the same there. This would be a Bernoulli trial, flipping a coin. Let's say we're looking at a study of a person. We're looking to see if a person lives or dies. Well, these are only two outcomes. There's a probability that they live. There's a probability that they die. It's only one case here. We're talking about one person here. One coin, one person. It's all Bernoulli trials. One event, one person. So depending on what you want to define, here we could have called this a success and this a failure. Here we could call this a success or a failure. Or sometimes we're actually interested in calling dying a success, which sort of seems a little morbid. It's not morbid, it's just the way we use these distributions. So you should get used to the notion that success doesn't always mean a good thing. Right? Just because you have live and die, don't automatically label this as live. Success, of course, we live. So, hurrah. No, it sort of depends. And that's what we're about to get into. Okay. Getting to the geometric distribution. So geometric distribution consists of n Bernoulli trials and here's the thing about geometric distribution. N Bernoulli trials, each trial is the same, meaning that the probability is not changing for each time we're flipping this coin. And more so, we call x a geometric random variable. X is the probability that we get our first success on the nth trial, or event, or person, or whatever we're dealing with here. So anytime we have these n trials, and all of them are going to be failures up until the last one is a success, then we've got this thing which is called geometric distribution. So an example of this might be flipping a coin. What is the probability that our first heads is on the 8th flip. So that means the first 7 are failures, and the last one is a success. This would be geometric distribution, and we could use this distribution to find out what this thing is. Let me give you one more example. Let's say hmm. So let's go ahead and say we're looking at we're taking a sample of patients, so a random sample of patients that are using this new heart medication, and we want to know the probability that looking at these patients that we sample, we have to get the first one that died is the 10th patient we looked at. So we look at the first one, he's alive, second one is alive, third one is alive, etc. The 10th one is the one who died. So again, the way you would label this, you can see that each person is a Bernoulli trial, could live, could die, only 2 options, right? That's it. Each person, we're going to assume, has the same probability of living and dying. They have the same condition, took the same drug. So what we would do is we would label this, the person dying here, we want the probability of our first success on the nth trial. We would actually label the probability of dying here would be a success. The die is actually a success here, because it's the thing that, whatever happens last here is the success. Okay. So let me go ahead and give you just 1 or 2 examples. But before I do that, let me at least kind of write some information about this. For the geometric distribution, the probability that x, the probability that the first success is on the nth trial, is equal to q, the n minus 1, times p. Or I think your book writes 1 minus p to the n minus 1 times p. Either way. They go further to give you some extra information. The expected value of this thing, the expected value is 1 over p. And I think they go further and tell you what the variance is. The variance of x is equal to what? I think it's p over p squared. Let me just double check on this. It is. Or if you'd rather, 1 over p, 1 minus p over p squared. Again, this is the same thing as q. Okay, so that looks good. So I think your book writes it like this. This is on page 120 if you're wanting to follow along. So these are things you should know. You should know this formula. You know what this is, how to use it, and what this is, and how to use it. We'll see that they're actually very easy to use. Okay. So as far as using this heads, probability, we saw a heads is a success here. We would say that it's a 0.5 chance of flipping a heads. So 1 divided by 0.5 gives you 2. So we'd expect 2 flips for our first heads. That's what that means. Let's get into some more information. Let's go back to this. Okay, so let's say we have this game, which is really, you keep playing or win, keep playing, stop or lose. So you win as long as you don't roll snake eyes. So no snake eyes. And you lose if you roll snake eyes. Okay, so let's go ahead and look at this thing. First of all, probability of rolling snake eyes. So I'm going to use S for snake eye. I'm going to go ahead and write this 1 out of 6. And the probability of not rolling snake eyes. Maybe win, keep playing this 5, 6. And again, the way you would do this is snake eyes. You can get a 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, a 5 and a 5, and a 6 and a 6. And then out of how many? Well, you got 6 choices for the first dice and 6 choices for the second dice. So you've got 36 total for the possible outcome. So you've got 36 in the sample space. You got 6 divided by 36 reduces to 1/6. That's how we get something like that. Alright, so let's go ahead and look at this thing. I would like to know, first of all, what is the probability that we go out or stop playing on the, let's go on the 4th roll. Okay. So here's what we'll do. We're saying that n here is the 4th. Right? You can look here, each roll is a Bernoulli trial. You could keep playing and win, or you could lose and stop. Right? Only one of two things is going to happen in this game. We have these probabilities. Let's go ahead and figure out which one's the success and which one's a failure. Again, just because we win, that's not necessarily a success. Just because we lose, not necessarily a failure. We say that to go out on the 4th roll, that meant the first 3 must win, and the last one we have to lose. So it's all about that last one. What are we doing there? That was our success. That's our P. So we go out, we lose, this is our P. So this would be our Q. If you look in the formula, here's how this works. It's just as simple as you have Q to the n minus 1, and here is 4 times P. So this is what? Q to the 3 times P, or 5, 6, P times 1, 6. So this formula actually should make a lot of sense if you look at it and really think about it. So we have 4 chances here, or 4 rolls here. So the only way to make it to the 4th roll is we have to win on the first one to keep playing, win on the second one to keep playing, win on the third one to keep playing, and on this last one we have to lose. So we have the probability of winning 3 of these, right? And then losing 1, right? Which should sort of make sense here. So this is failing n minus 1 times, so all the times up until you get to this nth one. And then that last one, we have the success. So this formula should make some good sense, and if you can make sense of that, it's just one less thing to memorize. Okay, so let's go ahead and look at this 5, 6, compute it, and then times 1, 6. We should come up with, well, if you're into decimal points, it's going to be 0.096. If you're into fractions, it's 125 over 1296. So this is what you would answer. 0.096. Okay. Let's go ahead and continue looking at this one. How long would we expect to play? How many rolls would we expect? Well, we would expect, again, our just looking at its expectation. We expect 1 over p. Right? So you have 1 over 1/6, or your p is 1/6, right? If you don't like that, you can do 1 divided by 6. You write this as 0.16666. Right? So if you want to 1/6 is 0.1. This probably will simplify your computation at least. So this is 1 over 0.166. And once you do this division, you'd end up with approximately 6. You might end up with 5.999 or something like that. That's okay if you're just off by a little bit. But you do actually stick this fraction and then invert it, you'll see you come up with 6. So what does that mean? That means that we expect that on average, playing this game, we should be able to roll 5 times before on the 6th time we roll snake eyes and lose. Again, this is a geometric distribution because we have all these failures, which are keep playing, until we get our first success, which is losing. Okay? Let's look at another kind of thing that we can do with those. Also, we didn't use this variance, but it's very easy to use. Just like this, we use 1 over p. We use the variance here as well. Actually, I suppose we can just go ahead and do that real quick. If p is 1/6, q is 5/6, or 5 divided by 6 gives us 0.833. So the variance of x, the variance of going out, is going to be q over p squared, or 0.833 all over 0.166 squared, or 0.833 divided by 0.02756. So you'd have a variance of approximately 30. So the variance here is 30. If you take the square root of this, again, this will put it back into the units, which means that we would expect to fluctuate about 5 rolls here and there. And we'll look at variance. It's useful for some predictive analysis a little bit later. Okay, so binomial distribution. Okay. Binomial distribution. So here's what a binomial distribution is. We have a fixed n, we have a fixed number of trials. Each is a Bernoulli trial, meaning that there is only a possible success or a failure, only 2 options. And each Bernoulli trial has the same probability of success, same probability of failure, and that changes from trial to trial. And we're interested in X number of successes. Okay, so they give you this bit of information, probability that X equals X equals K, there you go, is equal to, we'll write this and then I'll go ahead and explain it. It's going to be N take K times probability this, and then e to the n. And then we have the value of X is equal to NP. We look like it this way, and the variance of this thing is NP. If you do look in your book, and I should point this out, there is a bit of a typo in your book. If you do turn to page 123, see something that looks approximately like this. See if I can show you. This sigma, the sigma should actually be over here with the squared, so it should just be mu equals np, and then a bunch of spaces. Sigma squared, which is the variance, is equal to npq, and the standard deviation is the square root of that stuff. So if you want, you can change that. You should just be aware of that, though. These are the proper formulas. So you shouldn't have anything to do with standard deviation here. Okay. So before we can talk about this, we need to look at n take k and what this actually means. Briefly, let me at least go over this. 4 factorial, if you have not seen this before, is 4 times 3 times 2 times 1. So this is 1 times 2 times 3 is 6 times 4 is 24. 3 factorial is 3 times 2 times 1, which is 6. 1 factorial, of course, is 1. We define 0 factorial to be 1 as well. So even though it seems like this would be 0, we define it to be 1. So you get your calculators out for this factorial business. Okay, so this n take k means, precisely this, n take k, and it's written this way, n factorial over n minus k factorial times k factorial. And indeed, if you want, you can actually replace this with this whole fraction part here, if that makes it easier for you to use. Then of course you wouldn't have to do this memorization. So let's go ahead and just look and see what this gives us. Let's go ahead and use 5 take 3. So on the top we have 5, so this is our n, 5 factorial, all over what? 5 minus this bottom, 5 minus 3 factorial, times 3 factorial. 3 is our k. So if you prefer, you can label these things ahead of time. Okay, so what does this give us? 5 factorial all over 2 factorial times 3 factorial. Now in practice, we don't actually have to compute these and then do this division. It gets really large. What we can notice is 5 factorial, if I write it out, 5 times 4 times 3 times 2 times 1, and I write 2 factorial. 3 factorial I can write out, 3 times 2 times 1. We can see that a lot of this is going to cancel. 1 will cancel with 1, 2 will cancel with 2, 3 will cancel with 3. And so what I'm left with is 5 times 4 divided by 2 factorial, which is what? 20 divided by 2, which is just 10. So 5 take 3 is 10. Alright? And so we'll end up using this when we have these binomial distributions. Alright? Alright, so let's go ahead and give you an example of when we can use this, how we can use this. Alright, so we've got this test. It's going to be a 5-question test. 5-question test, all multiple choice. 1, 2, 3, 4, 5. A, B, C, D. Etc. So we've got 4 choices for each question. And we would like to know, what is the probability, if we Christmas tree this thing, what is the probability that just by guessing at random, we have exactly 2 correct? Okay, so here's the thing. Let's go ahead and look at this. Do we have Bernoulli trials here? We could get them right or we could get them wrong, right? It could be right or wrong. This one could be right or wrong, right or wrong, right or wrong, right or wrong. So we do have Bernoulli trials. We have 5 questions here. So this is our fixed n. And we're asking exactly how many did we get correctly. How many successes do we have? 2 correct, 2 getting correct. These are our successes. So this will be our P. And our wrong will be our P. Alright, so let's go ahead and find the probability. Let's look at this first trial. So again, these trials could just be just what we're talking about. Here we're talking about questions. Moving down the list. So the first question, okay, what's the probability of getting it right? There's one right answer out of 4 possible. So if we're guessing at random here, we can see that each one has an equal likely, we're going to go ahead and assume each one has an equally likely chance of being correct. So we're in this equally likely case. So we can do this number of correct answers, just 1 over total, 1/4. So if this is right, what's wrong? The complement of this, right? 1 minus 1/4, 3/4, or 3 wrong answers out of 4. So we have our P. If you'd rather, you can go ahead and convert these to decimals. We have our Q. So let's go ahead and work this out. This is the probability that x equals 2. That exactly, emphasis on this exactly, so we have equal. And so what we should have is what? N take k. So n here is what? N is 5. And k here is 2. Or x here is 2. So n take k, 5 take 2, times the probability of getting them right. We have 2 successes. How many failures do we have? Well, if we have 2 successes, we must have 3 failures. Okay. This is the number of ways we make them successful. Now let's go ahead and fill these in. 5 take 2. Putting this in, this will be 0.25 squared times 0.75 cubed. Of course, now we have to actually do this 5 take 2. So that'd be 5 factorial over 5 minus 2 factorial times 2 factorial. 5 factorial over 3 factorial times 2 factorial. And you can see that this will be evaluated exactly like we did on the last one, right? So we can write out this 3 factorial, just like we did down here, and do all this cancellation. Get 20 over 2 factorial, so it's just 10. So it's an interesting coincidence that, yeah, what we have here is 5 take 2 is the same as 5 take 2. Okay. So this is a bigger 10. Okay, so what we have here is 10 times 0.25 squared, 0.0625 times 0.75 cubed is 0.4219. And when I multiply it all together, it should come out with 0.2637. So it's something like that. So it's important to notice the difference here, because on the quizzes and tests and things like that, it won't be obvious. It won't say this is a binomial, so that is a binomial distribution versus geometric. The difference here is I'm not saying I have I'm not having the last one is correct. I'm just saying any two are correct at all, right? So I have a fixed number. It's nothing to do with I go until I get my first correct answer. That would be geometric. Let me flip back just for a second so we can talk about this expected value here. Expected value here, here's what this means. 5n, which was 5, times the probability of being right, I'd have 1.25. N times 0.5 times 0.25 is 1.25. So on this question, on this test, I would just expect to get about 1.25 correct. So 1 to 2 questions correct. That's what I see most often. The variance of this thing would be n times p times q. So what I end up having is 5 times 0.25 times 0.75. Now I end up with 0.9375 for the variance. Okay. Let me do one more kind of variation on this, just so you can see a little bit different. What is the probability that 0 are correct? Again, this is just the probability that x equals 0. So this would be 5 take 0 times the 0 that were correct. So p is a success. So we have 0 successes. Then we had 5 that are incorrect. You can work this out for yourself and confirm that that's 1. P to the 0 power is 1, and then q is 0.75. We can use this. That is 0.75 raised to the third power gives us 0.421875. So that's the probability that 0, exactly 0 correct. Let's look at something else here. So if I have the probability of at least 1 is correct, the key here is whenever you see at least, this should be a key word to go ahead and try to think as far as the complement. The complement tends to be easier when I see these at least, or at least it can be easier. When I have at least 1, what I'm saying is, of these 5, at least 1, so I can have x is 1, that's a possibility, right? Plus the probability that x is exactly 2, plus the probability that x is exactly 3, and I can continue to go. X is 4, and probability that x is 5. So we saw with 0, and we did 2 exactly already. This is really painstaking to do this individually like this. It's much easier to think about this instead of like this. As well, let's look at the complement of this. 1 with probability that not at least 1 is correct. Well, what's the complement of at least 1 is correct? Well, that none are correct, right? None are correct. But we already found that, right? We found it up here. It's 0.421875. So we don't have to do a lot of work here. It's just 1 minus 0.421875. Which would give us 0.578125. If you really want to, you can check yourself out on 1, 2, 3, 4, and 5. Add this up. You should come up to something close to this. You'll probably get off just by rounding error. But just be cautious there of those leaks. Alright then, I do recommend you looking at the homework. The suggested homework is there for a reason. You'll see that the quizzes very similar. They ask the same sorts of things that are on the homework, so if you can do the homework, you should be fine on the quizzes. Also, make sure that you guys are clicking the true-false question at the end of these lessons. That way you do get credit for the actual lecture. We do take attendance, so I think I saw one of you had not done that, so just wanted to remind you. Alright, and again, as always, if you have any questions, just send me an email or anything, and I'll be happy to help. Good luck to you, and I'll see you next week.